Welcome to this Quantum Security and Defense presentation, Building Quantum AI at Scale, and thank you for being a valued member of our community.
Dr. Sonika Johri is founder and CEO of Coherent Computing, a company focused on building software platforms to enable users to take advantage of the rapidly expanding capabilities of quantum hardware. As a principal researcher at IonQ, she led a team working on quantum applications R&D for clients including Hyundai, Fidelity Center for Applied Technology, GE Research, Goldman Sachs, Airbus, and Thomson Machinery. She has authored 40-plus publications, recently focusing on cutting-edge quantum algorithm demonstrations in the areas of generative and discriminative machine learning, quantum chemistry, optimization, and condensed matter physics across a variety of quantum hardware platforms, as well as developing frameworks for quantum benchmarking. She has a PhD in theoretical condensed matter physics from Princeton University.
You would need fewer qubits than you would need the equivalent amount of classical hardware. And then, of course, there's some very unique things that can happen when you combine quantum models with other quantum transforms, right? Like, when you train a quantum model, you don't just have the model by itself. You can use certain quantum transformations, like, the inverse of it, or you can combine it with a quantum Fourier transform or Hamiltonian simulation, and all kinds of magic can emerge from that. And we're just beginning to understand all of that. So there's lots of exciting reasons to study and try and build quantum AI at scale. And then at the other end of the spectrum, we also know that quantum hardware is very steadily scaling. So there are many different quantum hardware backends that are being built commercially, and these span, whether they're transpons based on superconducting technology, or spin qubits or ion qubits. They're all, there are several different companies that have. Oh, can you still see my screen? Yeah, so there are several different companies that have that are building these hardware platforms, and they've all put out their different roadmaps, right? Very ambitious, and I don't expect that all of these roadmaps will pan out as as advertised, but still one can't deny that all the different quantum hardware backends are steadily scaling. However, this presents a dilemma to anyone who's building applications on these hardware, because it turns out that quantum programming at the moment requires you to know at a very detailed level the idiosyncrasies of each hardware platform. And then to add to that, every time new hardware comes out, it causes some of the software programs that have been developed to become obsolete. So this is not a good situation. To kind of address this kind of messy situation at the hardware level, at Coherent Computing, we are building what you can think of as the Android for quantum computers. So we call it Red Cedar, which is a quantum operating system that is designed to be scalable. So it should scale to thousands of qubits. It should be modular. So it has, by modularity, I mean that it's composed of these different building blocks, right? So at the bottom, you have hardware-specific layers, and at the top, you have hardware-independent layers. And the bottom of the quantum OS, or quantum computing software stack, it interfaces with different quantum hardware APIs. And on the top of that, you have these hardware-aware quantum circuits. And on top of this quantum OS, you have these APIs that integrate into different domain-specific workflows, which are in turn built on top of quantum application libraries, which are built on top of this quantum programming framework. Which right now we're calling quantum structures, which in turn can be compiled down to quantum circuits. And this modular structure also allows for the OS to be portable between different hardware frameworks, because you can keep the higher level programming layers as they are, even if you switch out the lower level hardware backends. And of course, it allows it to be user-friendly, right? So if you are, for instance, a genomics expert, then you don't really want to know about, how to program qubits based on ion traps, right? You want a lot of routines that will quickly allow you to implement a solution that is relevant for your domain area. And this kind of approach allows you to do exactly that. And so some concrete goals that we have for our framework is that it should be scalable to 1,000-qubit algorithms. It should be portable across technologies, like I mentioned. And you should be able to get to it at your level of knowledge. And then, very importantly, right now, when people program quantum computers, they program it in terms of what you can call quantum assembly language. And we want to move away from that in order to build quantum programs at scale. And of course, interpolate between near-term and fault-tolerant quantum computers and efficiently integrate with quantum hardware platforms. So with Red Cedar, Red Cedar is a general quantum OS. One of the first things that we are going to build, that we are building with that, as I mentioned, is our quantum AI platform. And that right now has the ability to take in all kinds of data, which can be either text-based data or some kind of scientific data, load it into quantum states, deploy a bunch of quantum models to be trained. And these models can be purely quantum models, or they can be in a hybrid quantum classical setup. You can train these models and you can perform inference upon them. And we've built into our framework the ability to combine both quantum and classical data transforms. So classical computers are good at different things than quantum computers are, right? So classical computers are very good at, for instance, arithmetic. Quantum computers are good at modeling high-dimensional probability distributions. And so we have, at the software level, some custom interfaces which can kind of interface these two very different kinds of data transformation. And there's some other features that we've built in, right? I won't go into too much detail, but basically the way that we have set this up for quantum AI is that you can maintain both speed and privacy while training your models. So you don't, so let's say you have some data set, you don't need to provide your data set to the provider. You can encode your data into quantum states on your end using the speed that comes from doing so. Really, so far, whatever I've talked about, you can find in a lot of other quantum machine learning platforms, such as PennyLane or Qiskit as well. Really, what is our secret sauce in this quantum AI platform is going to be a bunch of proprietary techniques that are implemented in software for foundational properties of quantum machine learning. So for instance, things like constructing models with universal approximation properties, efficiently loading classical data into quantum states, as I mentioned, guaranteeing model training to high accuracy, and scaling of quantum models without encountering or without getting stuck in zero gradient regimes. And so I'll go over some of the secret sauce in a bit more detail. So some of these techniques are in this paper, which is currently on the archive. You can go take a look if you're more interested. So the first technique I'll talk about is this bit-bit encoding, which is a technique for loading classical data into quantum computers, right? So let's say you have some kind of classical data set, which could be a data set of images, or it could be a data set of proteins, right? Typically, data loading in quantum machine learning or quantum AI is a step which is kind of inefficient, right? So our idea over here is that what you should do is extract only the most predictive bits from your classical data set. And then you assign more bits to those dimensions of your classical data that have higher predictive ability relative to the learning task. And so as you increase the number of qubits, you're also going to increase the amount of data you're encoding into your quantum state. Then the next kind of technique that we have in our platform is this ability to do optimizer-free training. So when you're conventionally training a quantum model, people typically use optimizers such as Adam or some kind of gradient descent. And these optimizers require setting several hyperparameters such as learning rate using educated guesses, and then there's no guarantee of convergence. What we've shown in our paper is that quantum models can be trained without using an optimizer at all. And this can be done if instead of trying to update all of the parameters of the quantum model at the same time, you try to find the exact local minimum of one parameter at a time. And using these techniques that are based on the trigonometric structure of the quantum model's cost function, what you can show is that these models can be guaranteed to train to a minimum. And so what it does is that your model will only stop updating when a minimum is reached, right? So you don't need to keep guessing whether your model has trained perfectly or whether it can train a bit better. And then the third important technique that we have proposed in our paper and also implemented in our platform is the subnet initialization technique. And what this allows you to do is initialize the training of a larger model based on first training a smaller model. And this is important because if you try to train a very large quantum AI model from scratch, what you're going to run into is the zero gradient problem, where at the start of the training, your gradients in all directions will be very, very close to zero, so you will not be able to proceed with the training. So instead, what we showed is one can exploit the unique nature of quantum transforms to first train smaller models, which we call entanglement nets, and use it to the corresponding gates of a larger quantum model, and then add new gates where you're setting the new gates to identity. And we validated the performance of this technique on the MNIST dataset. And so finally, the results of this can be seen in this example I'm showing of training on the MNIST. So for those people who may not know, so the MNIST dataset is a dataset of handwritten digits from 0 to 9. And over here, NQ is the number of qubits, right? So the green curve, for instance, is a training on 6 qubits. Red curve is training on 8 qubits. Blue curve is training on 10 qubits, and so on. And on the y-axis is the loss. So as the model training proceeds, you want to reduce the loss function, right? And on the y-axis is the number of updates of the parameters in the model. So what you see is that the training of the large model of the 10 qubit model starts where the training of this model left off, right? And then the training of the 12 qubit model starts where the training of the 10 qubit model left off. So what this kind of shows you is that the training of the small model becomes a critical step in the training of the larger models, right? And from that, what you can see is that it means that near-term quantum computers can also contribute to building large models. So let's say you have a 40-qubit quantum computer this year, right? Or something that has 40 logical qubits, let's say. So you can build a 40-qubit model, right, which next year can be used to train a 60-qubit model, which the year after that can be used to train a 100-qubit model. So it's a way of making use of near-term quantum computers, right? Because often people say that you can't do anything with quantum computers unless they have 1 million qubits. Anna, are you saying that my time's up?
Yes, if you could slowly.
Yeah, okay, so Yeah. Okay, so I'm almost at the end. So I'll just end with saying that, so we're building this quantum AI framework using Red Cedar, our quantum OS. And then we're also starting to build out a specific application area, which is quantum omics. And hopefully we're going to start publishing some use cases and studies using our quantum omics platforms in the next couple of months as well. I'll just end there, Anna. I'm happy to take questions.
Yes, we have questions. Thank you so much for the talk. I'm sorry I had to interrupt it. I was not sure how long is your presentation because you mentioned it, and but it was lovely. And we have questions coming in. First one is from Bill. There are two questions from Bill, but the first one from Bill was, does this AI model protect data any different than other AI, DeepSeek or Copilot?
So I think with quantum machine learning, we have not started to ask those questions yet, right? But I would expect that some kind of analysis is required to answer that kind of question. But, quantum AI is sufficiently different from classical AI, right? The more we learn about it, right, the more different kinds of properties emerge, that there may be the answer to this question may be yes, right? That the data may be protected differently, but it's just that we don't know yet.
Thank you. And then from Shabib, how is Red Cedar different from Munich quantum software stack? How do you see this converge?
I have not personally used this Munich quantum software stack, so I don't know. Would you like to tell me a little bit about what the Munich quantum software stack involves? Maybe the person who asked the question can say a couple lines.
Yeah, actually, this MQ's SS is uh, a high-level integrator for quantum computer hardware providers. So they are also building a similar software stack with which quantum integrators can integrate their hardware directly to the stack, and they are trying to standardize this whole setup. So I was just thinking, how does this consider different from them?
So then it sounds, a bit similar to also like what IBM, for instance. So there are many people actually trying to do this right now, right? We've put in some effort into our platform. All the properties that I mentioned, that it should be very modular, so you should be able to change one part of the platform without it affecting the others, right? It should be scalable, so really we want to be able to scale to 1,000 qubits, and we want to build a lot of libraries that interface with really end users, right? That may have very little knowledge of quantum physics, right? So I think we are pretty happy to collaborate and incorporate, especially if there are any open source tools out there. Yeah, so I would love to learn more about this effort. It sounds like it's going to be open source.
The next question from Shuveen. Do you need to train your model on quantum computer or just the classical simulator?
So of course the model should be trained on quantum computers, right? So currently, what I showed, up to 16 qubits, you can train it on a classical simulator. But what we want to do ultimately is train these quantum models on quantum computers, right? So when you go to 40, 50 qubits, you will not be able to do it on classical simulators anymore. But there are some very interesting techniques which show that you can train your model on the quantum computer, right? But then once it's trained, you can use certain approximation techniques to at inference time deploy it on a classical simulator or some kind of tensor network simulator, right? And I think that opens up some very interesting use cases. So for instance, if you want to use quantum models for, let's say, self-driving cars, right? Now you don't really want like a quantum computer to be installed in a vehicle. But what you can do is that, once you train the quantum model on a quantum computer, the approximation of the model can be deployed on a GPU, which can be in a vehicle, for instance.
Thank you, Sonika.
Thank you for watching this presentation, and thank you for being a valued member of our community.